Hi everyone, welcome to NLP with HuggingFace tutorial. In today's tutorial, we are going to see how you can train named entity recognition. We will be using here HuggingFace models. I'll be showing you how NER works and then how you can fine tune your model for NER training. So you need to first understand that what is NER. But before that, let me hide this so that we can get more space, and other than that, probably I should be putting it into a full screen for better screen. So here we have NLP with HuggingFace tutorial. Now we need to first understand what is NER. NER is also known as a token classification. You might have heard about the classification where we do the class classification or sentence classification or sentiment classification. But NER is a token classification. So the token classification means a sentence is broken down into the tokens and then we classify those individual tokens there. Once all these individual tokens classification is correct, then we say that for whole sentence classification is correct, otherwise it is wrong there. So this NER stands for named entity recognition, which is a natural language processing technique used to identify and classify named entities. Any named entities, currently we are seeing here people, places, organization, dates, and many more. So here are a breakdown for NER in 5 steps, which you can see. NER in 5 steps, how it works. So in 5 steps, it works like text input. You give a text input. Thereafter, a tokenization is done there. So we classify this token. That is why it is known as a token classification as well. On this token, entity recognition is done. And thereafter, the classification is done. Alright. So there are actually a rule-based method. Either entity recognition is done or machine learning model like. Rule-based methods are not that much accurate, but nowadays machine learning models are very much accurate. Then a final classification is done. Thereafter, after this final classification, this output is produced there. Alright, perfect. So how would you see this in this image? In this image, you will see this as here token. So in this token, you have Jeff Dean is a computer scientist at Google in California. Then you have here tagging. So Jeff Dean is here person. Now before this person, you have here prefix B and I. Then there is OO and then OO and then again O. Then again you have here Google and then here you have organization. A prefix is used here B and then O, and then in California it is tagged as location and the prefix is B here. So what are these prefix? So these prefix B, I and O, these defines that when your token starts or end and when token is included in the previous token itself, and when token does not belongs to any classes. So B means begin, I means inside, O means outside. So this technique is known as NER classification format, which is also known as BIO format or IOB format. Beginning, inside and outside. So beginning says that your NER starts from this place. And then I says that if I comes immediately after this B prefix, that means this I will go along with this B in final prediction. That's when this Jeff Dean will be predicted as person together, not the individual person Jeff and Dean. Alright, because B and I. So B and I goes together if there is no token between these. Thereafter this O says that it does not belong to any token. So whatever the token we have currently. So currently we have person, location and organization. So this token does not belong to person, organization and location. Thereafter for this we have B organization. Then we don't have any following I prefix. That's mean this Google as a stand alone here as organization. Similarly, in California, we have here a B. There is no postfix here as I. That means this California is here location as standalone here itself. Alright, so you understand this with this following graph in more better way that you have here an input. Input says that my name is Omar and I live in Zurich. You see there, here we just saw person, organization and location. But your named entity classes or token classes are not just limited to these three. It can be anything. So here we have here, my name is Omar and I live in Zurich. So token classification model runs at the HuggingFace. Then it comes here, my name is Omar. So Omar is declared or classified as a person, and then I live in Zurich, and then this is classified as location if you go by this. Otherwise it is GP, that's the geographical location here. You can see here a demo. I have given a link for the demo itself. You just need to click on this. Now you will see here a demo. I'm gonna give here the same name which we had seen earlier. Let me just see it here. Okay, so the same sentence which we had seen earlier, the same sentence was like Jeff Dean is a computer scientist at Google in California, something like this. Alright, and I'm gonna select here everything, all these. So previously we had seen 3 and 4 entities only, but now in this sample what we are seeing here in this passive sample, we have many more entities like person, okay, and NER, organization, GPE, then we have here location, product, event, work at art, language, date, time, percent, money, quantity, and ordinal and cardinal. Alright, perfect. So by the name you understand all of these, but this NER means nationalities or religion or political group. Alright, so this is nationalities or religious or political group. Let's go ahead and run this. So Jeff Dean is classified as a person together, is a computer scientist at Google organization and California as GPE. Now if you see what we had seen here, B and I, that's what I was telling you there, that B and I, so this was classified as person B and this was I. Now at the final output, all these combined together. So it becomes there a person, Google and California. You can do a little bit more. Like let's say I'm gonna say here latest news, and then I'm just latest international news, and then I'm just gonna click on there. Let's say I click here, and then I'm just gonna take this whole thing from here. Then I'm gonna just copy it from there, and then I'm gonna put that news here, and thereafter I'm trying to find out named entity. So how it does there? It says that the Canada is GPE, Saturday is a date, 2 is cardinal number, tens of thousands is again a cardinal number, and just days is date here. Now you see how good this named entity recognition is working here. So if you have your own data, let's say you want to do resume parsing, or you want to apply this in some search system or some legal document classification, or in some other kind of the text analysis, you might have your own data for NER recognition. So you can train your model. That I'm going to show you how you can train your model to classify to build these NER model. Alright, let's go ahead and get started with IOB NER format. So you see this inside, outside and the beginning NER tagging format, which we have already seen, and it stands for inside, outside, beginning tagging. John Smith lives in New York and works for United Nations. This is again another example. So you see John Smith, since these are a single person, so the first token is classified as beginning, second token is classified as inside, so this one is inside of this token itself, so these will go together at the final output. Lives in New York. Again, this New York, this location is starting of this New York, and this token is inside this new, so it becomes here New York. Thereafter, work for United Nations. Again here beginning, and this one is inside of the previous token, that is the United Nations will go together when we do the final classification. You can see the tagging format here at the Wikipedia. So in this Wikipedia, it says here, it describes in a little bit more detail, but this is out of scope of for the current lecture. So we understood that what is NER, how NER works. We have seen the demo of NER and the tagging format. Now we are moving to the real stuff. Real stuff is what is the transformer, and then how this transformer works. Thereafter we will start collecting the data, and then we will start doing the fine tuning of our model. So this transformer architecture is a key innovation in mechanism of the self-attention. So self-attention model was introduced around 2017 and 18, and the name of that paper was the transformers. So in the transformer, it was like there, in fact, attention was even before that, but in the transformer, it was utilized in a little bit more better way. So this transformer utilized the attention. So the main component, or you can say the heart of this transformer is self-attention. So inside that there is the self-attention. The self-attention means when you provide here the set of the sequences, then it automatically find out which sequence is, which token need to pay more attention on other token. Alright, let's say a person lives in San Diego. So a person will be attached more with the San Diego because there is more attention. Who lives in San Diego? Because that person lives in San Diego. So you will see there a lot of correlation or the attention between the person and the location. This is, I'm saying it in more like a simple way, how this self-attention mechanism works there. So after this transformer, a lot of transformer models came like GPT, BERT, GPT-2. Thereafter, RoBERT, DistilBERT, XLM, GPT-3, and nowadays we have GPT 3.5 and GPT-4. All these models uses transformers itself. There is another important model introduced by the Google, that was the T5, and there is the GPT-Neo. It was like a variant of the GPT-2, more powerful than GPT-2 and less powerful than the GPT-3. The GPT-Neo is. So you see there is transformer architecture here. We have seen this in our previous lecture when we were seeing a token when we were doing classifications. Now in this transformer architecture, you see there is a token, there is a sentence. These sentences are divided into token, then token encoding is happening here. Thereafter the token embedding, then positional embedding also goes along with the token embedding, because we need to preserve the information of the positions for the token. Thereafter, the encoder stacks are there. That's where the self-attention mechanism works here inside this encoder stack. And thereafter, these hidden states produce the final output. So this is where you get the final embeddings there. Thereafter, it comes here the decoder, and then again hidden states and the classification and the token predictions. Now you see transformer, the actual original transformer is built with encoder stack and the decoder stack. But we actually do not need all these encoder and decoder together. For some reason, like let's say you want to do translation, language translation, then you just need the decoder. You want to do the classification, then in that case you need an encoder. Encoder works better. This classification works better with the encoder only model. Like we have a DistilBERT and the BERT model. All these models are actually mainly used with the encoder. I mean, these models are used with encoder, all these models which you see here, BERT, Roberta and the DistilBERT. But you see the GPT and the GPT models are used, mostly they use these decoder stack, and these T5 models are also used for decoder stacks because these models does these translations, language translations there. So you see there the token classification is something like this. So you have your encoder stacks. You see there this encoder stack is represented here, the transformer encoder. In fact, this whole thing is represented as a transformer encoder. So this tokenization is done here at the outside itself. So you can say that this particular part is shown here itself, and then these embedding and encoding stack are combined together as the transformer encoder. Thereafter, you see there the hidden states are here, and then finally a linear neural network, or you can say here a fully connected neural networks are applied here for final token classification. For each of these tokens, a final classification is done here. So these are CLS. CLS says that it is starting token, and then here it is ending token. So CLS and the separator will not be tagged here. Krista, you see there the Krista. So in this Krista, CHR, this is the beginning of person, and then it is saying that ignore this one, that's the IGN. So IGN ignore means whatever is ignore, you can combine these together, because anyway in tokenization we know that if there is the double hash there, that means this token we need to include with the previous token itself. So even though if we ignore this, now we know that this is the part of the previous token, so this whole thing will go that as the beginning of this person. Then this says that this is the inside of the previous token. That's when this crystal lange will go together. Because of this hash, these will go together. Because of this inside person, these two and this one, all these three will go together. Thereafter this lubs, that's the outside of any entity. Thereafter the beginning of the location, and then the inside of the previous token, that's the San Diego. That's how the token classification works here. Alright, so we will be using here CONLL-PP dataset. This dataset is variant of the CONLL 2003 NER dataset. In this dataset, with the help of manual intervention, around 6% sentences were corrected. I mean, some part of the sentences were corrected because of there were wrong tagging. So the tagging were corrected manually. So a little bit more better version of this dataset is CONLL-PP version. And this CONLL-PP version you can see at the HuggingFace. So at the HuggingFace, I'm just gonna click on here, and then you see this dataset here. So CONLL-PP dataset, this is used for token classification. This is subtask of named entity recognition. Dataset is available in English language, and it only contains English language because it is monolingual. And number of categories are here. I mean, total numbers here you see are greater than 10k but less than 100k. So this is some kind of attribute. With the help of this, you get to know that what it is all about. So this dataset have tokens. We will be interested in tokens and NER tagging. It has 3 split: train, validation and test split. And we will be interested in token and NER tagging only. You can apply the same concept for part of speech tagging and the chunk tagging. So we don't need this part of speech and chunk tagging. We just need NER tagging. So for that we will be needing this. For that we will be needing this column and this column. Now in the first column it says that EU rejects German call to boycott British lamb. Now you will see the difference what we had seen earlier during our demo. In demo we had seen this data, but what we are seeing here, we are seeing here tokenized data. That's when data is already tokenized here. So once the data is already tokenized, then you need to pass in your model that my data is already tokenized. You do not need to tokenize this. Then in NER tagging, it says that 3, 0, that's when this goes as 3, there is 0, 0, and 7, 7, and all these. So you might not understand that what is these 3, 7, 0, 0, all these stuffs are there. These stuffs are actually those 7 classes which we had seen earlier. So those 7 classes are there. Just let me show you here. So, okay, so these 7 classes, do you remember that for location, person, and organization, we have beginning and insight. So 2 for each, there is 3. Location, organization, and person, that's mean 2 into 3, that's the 6, and 1 plus 1 for outside. So these 7 numbers which you see that, these are actually made for that one. But here it seems like there are total 8 numbers, but don't worry, we will see all these stuffs when we download this data, then we will do the analysis of this data. Alright, so we have seen our data. Now we know that how our data look like. Here is some example which I have pasted here. What got corrected in Con LLPP dataset versus Con LL 2003 data. For example, for this it was tagged as person, but it was actually location. This one got corrected, and maybe something also got corrected here itself, that NER tag, POS tagging, and the tokens. All right. Okay, so this is our data. Now we need to download our data. To download our data, we need to install transformer, accelerate, and dataset. We are going to download or install latest version of the transformers, accelerate, and the datasets here. I am not connected as of now to the GPU. Here you see change runtime. Currently it is CPU. The reason is this is YouTube video. This takes a lot of time to make this video. And by that time, I do not want to connect this with the GPU. Otherwise, unnecessarily, I will consume GPU credits. I need GPU only during training, not for writing the code. So I will connect it. I will first connect it with the CPU. Once all the coding is done, in the last, when I'll need to train my model, then I will change my machine from CPU to GPU, and then I'll train my model. Alright, so currently it's a CPU. Let's go ahead and run this, and then I'm going to just hide this one so that we can get here a better space. This will take a while to complete installation. We have to wait for some time. Alright, installation is done now. We need to now import necessary libraries, and then we have to download the data. So I write here import pandas as PD. It is asking to save. I'm just gonna save this. Thereafter I write here, okay, wait a second. Alright, save your changes. Then I write here from, okay, from datasets import load dataset. Alright, so we have imported load dataset. Now you need to just keep the name of your dataset. It will automatically get downloaded on your machine here. So I write here data is equal to load underscore dataset. Inside this I need to give the name of the dataset. Name of dataset is con LLPP. I give here con LLPP. It will just download the data. Thereafter you can see the total number of splits available in the data. As I told you earlier, there are 3 split in the data: train, test, and validation split. It will take a while to download. Now you can clearly see it has train, validation, and test split. Like we had seen in our original, in our data set here at the HuggingFace, it has similar columns there: ID token, POS, chunk tag, and NER tag. These are the token. These are the columns. So we are interested in tokens and NER tags only. We will not use ID, POS, and chunk tags. Alright, once you have that, you can run it again here just to avoid or remove those download bars there. So this is the dataset dictionary. This is a special function or method in HuggingFace, which have three keys: train, validation, and test. In these three keys, again, this train is a kind of the dataset. This dataset have a features and number of rows. Features, number of rows, features, number of rows. Alright, let's go ahead and see our train data. So I write here data train dot features. So what do we see here? In data train dot features, we see here value type is string here, tokens, sequence token where the data type is a string, length is -1. Okay, anyway, so you see this one is a string value, that is the ID. So whatever the ID, we see that this is a string. Then the data type is here sequence, 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 and sequence. For all those three, there is sequence. And in POS tagging, we have class labels. You see there, these are the class labels here. So these are the class labels for POS, chunk tagging, and here we have for NER tagging. Now do you remember I told you that we had there total 8 because it was 0 to 7 numbers were there. That's when there are total 8 NER. So 7 we counted, that was correct. And I think 2 more got left here, that is the miscellaneous. Alright, beginning of miscellaneous and inside the miscellaneous. That means that is not 8 but in fact 9. You count this 1, 2, 3, 4, 5, 6, 7, 8 and here 9. So there are total 9 tokens here. Earlier we had seen person, organization and location, 2 tokens for each, that is the 6, 1 token for outside, that is the 7, and then the 2 tokens for the miscellaneous, that is the beginning and inside. Alright, let's go ahead and get the first data or the first sentence or the first token sequence from our train sample. So I write that data train, and if I write here a colon, that's mean we are going to get all the sequence, I mean all these training sequence, but we are looking to just get one. So I write here okay, so we are getting everything. Now to get only one sequence, probably I need to see this if I can get it like this. Otherwise we have to convert it with the pandas data frame just to know it better. Okay, so this one is not working. Let's go ahead and convert these to pandas data frame. So I write here pd dot data frame. So this will become now pandas data frame because anyway the dictionary. So if you pass a dictionary to data frame, it becomes a data frame there. We need here just tokens and NER tags. So I write here tokens and then NER tags here. Thereafter I'm interested into just first token that I get with ilock 0. So I'll be getting here first one only. So it says that EU rejects German call to boycott, you see there, boycott British lamb. Alright, that's the token, and then here we have NER tagging. Now if you match these with these given name, you would be able to identify that how it is matching. So 3 is 0, 1, 2 and here is 3. That is the organization. So EU is organization, tagged as organization. Second one, reject, is tagged as outside, that is the none. Then the German is 7. 7 is 0, 1, 2, 3, 4, 5, 6 and there is 7. Alright, so this one is miscellaneous because this German is not a location. Alright, this is miscellaneous. call to boycott British, then this British is again here tagged as miscellaneous there. Alright, that's how this tagging is done here. So now on this we will train our model. Now we need to do a little bit more analysis and then we will write our code to train the model. So we need to first get the tagging. So the tagging I get here, the tags equal to data train, and then inside this train I write here dot features. Now if you check this dot features, if you print these tags, you will get it something like this. These are all the features. But now I want here just NER tags. So inside this I want NER tags. Inside this NER tags we have got all these stuffs here. Thereafter these are tags here. Thereafter we need to get here the name of these tag and the index of these tags. So I'm gonna create here two more dictionary where I can convert index to the tag and the tag to index. That means where I can convert these index to corresponding tag and these tag to corresponding index. So for that purpose I have to write here a for loop, and also I need to write here enumerate. So I write here enumerate, that's when it is going to iterate over these tags. Thereafter I write here for idx and tag in this. So what happened here, once we do the for loop on enumerate tags, so the first variable takes the index, that's mean the number of times for loop has ran, and this tag takes these values. Once you have all these, we are going to use here a comprehensive list technique. So it's something like this. A comprehensive list technique will produce these data here itself. So I write here idx and then I write here tag. So if you write it something like this, then you will get there add id to tag there. Alright, and it says that this is not iterable because this tag which we had here earlier, for that we need to also get the name of the classes actually. So this one we need to get here, that you can write it tags dot names. So you will okay, it says that it does not have any names there. Okay, wait, now here it is actually the feature. Once you get this tags dot feature, thereafter you need to write here names, then you will get the correct things here. So basically what I can do here, I have to enumerate tags dot feature dot names, and then I'll get the correct output. Okay, this should be idx. So index to tagging comes here. Now you can identify it immediately here. 3 is organization and then 7 is miscellaneous here. Miscellaneous. Thereafter I write here index to tag. It's like that. Thereafter I write here tag to index equal to, and then I copy this whole thing from here and paste it here, and then I write here tag, and then I write here idx, something like this. So we have here tag and idx. For idx tag, in enumerate tags dot feature dot names, we have here our index to tagging and then tag to index. Perfect. So we have got here everything. Now let me show you another way to achieve this. Let's say you want to get these values, these things, I mean these index to tagging directly. How would you get that? So this tag you have to actually modify. So for that I'm gonna write it something like this so that I can adjust that there itself, and then I can remove this here. Okay, so index to tag and tag to index is the same thing like we had seen earlier. It's managed in the same way. Now if you want to get these without writing these, how would you get that? You have these tags. So these tags have two extra method here. The first method is int to str here. In this, if you give here any name, in any integer value, it will give you its name here. Right, into str, that's the 3, it gives here this one, organization. Alright, perfect. Alright, let's convert our the numbers, indexes into the tagging name. So we need to write here a method or a function. I write here def create underscore tag names, and then I'm gonna pass the data in batches. So I write here batch. Thereafter I need to get here a dictionary named as temp, and in that I'm gonna give here name as NER tags str. So as you saw our training data, in training data we had our NER tags as numbers or as index. Now for better representation we want these index as the string names. So for that purpose I write here temp equal to NER tags str. Thereafter I write here for idx in batch. You check here in batch. Now I need to enumerate these NER tags here. So I write here batch and then NER tags here. So once enumeration is done for this, so I'll be getting here index. Then you can simply use those tags dot int to idx, this formula, directly to get the string name there like we had seen earlier. So now you can use these int to idx or index to tag directly. So either you can use this one or this one. So whatever you use, this both will work here. So tag dot int to idx, then you have here idx. So with that you get here tag name. In fact I should give a name as tag name. Thereafter I return this tag name. Okay, so this is the method to get NER tag names. Now we need to apply here a map function on our data. So it will automatically do for all the split. So this map function will get applied to our train, test and validation. Alright. So I need to just give here our method name. So the method name is create tag names. It will automatically get applied on training, test and validation set. Now if you check your data, okay, wait a second. This should be int to str, like here. Let's go ahead and run this and then this. So the mapping is getting applied for all the split. It is applied for train, test and validation. You have your data. Now if you print your data, you will be seeing here additional column which is NER tags str. Now if you check this, let's say you copy this whole thing from there and then you paste it here and then you just copy that from here. Alright, so we have got here beginning of organization, beginning of miscellaneous and then beginning of miscellaneous. So simply it copied these index as str or its respective NER str values here. So we will be using this and this for our model training. Okay, so Now our data set is ready to get trained. Let's go ahead and build our model. So I write here model building. All right. So in the model building, I write here from transformers import auto tokenizer, something like this. Thereafter, I write here model checkpoint equal to, I'm going to write here DistilBERT base caged model. Alright, so what happened here, we are going to use the distilled version of the BERT base caged model. You just simply copy this, and if you paste it here, you will be able to see this DistilBERT base uncaged model. So there are many models. You can check it here, DistilBERT base caged model. So this model is a distilled version of BERT base model. It was introduced later after publications of the BERT model, and then the process of distillation can be found here. The model description is same as the BERT model. Now we can directly use this DistilBERT model as its name suggests here. So that name we have already written it here. So that model checkpoint will get down, the tokenizer and model will get downloaded from this location. Now let's go back again in starting just to understand that how this whole process is gonna work. Do you see here, we had our data, thereafter tokenization and the encoding was done. So the same thing we have to do here. That's why we imported here auto tokenizer. So we need to tokenize our data in the same way or for the same model which we are going to use for the training. You cannot use a different model for tokenizer and training. So that's why I imported here auto tokenizer. So this auto tokenizer will automatically find out DistilBERT base caged tokenizer, and then it will tokenize our data. It is just for testing purpose. Alright, so here we have our tokenizer equal to auto tokenizer, and in this I'm writing here from pre-trained, and then I write here model underscore checkpoint, something like this. So you have model checkpoint equal to the DistilBERT base caged, tokenizer equal to the auto tokenizer dot base pre-trained model checkpoint. It's something like this. Let's go ahead and run this. Now once I run this, it's going to download some parameters like configuration files from the internet. Now this tokenizer is ready to get used here. Now tokenizer comes as fast tokenizer and slow tokenizer. That's mean normal tokenizer and fast tokenizer. You can check that tokenizer.isFast. It says that it is fast tokenizer. So the fast tokenizer works very fast. So it's lightning fast. You can say that for tokenizing task. It doesn't take much time in tokenizing. Our data set currently which we are seeing here, it is just like 20,000-30,000 data set. It's okay. But when you have a billions of the data points, then you need to have a fast tokenizer there. Okay, let's go ahead and check our the tokenizer from our sample data. So the sample data is here. If you check this was our sample data. So this sample data now we are going to check here. Let's say we have our data, then we have here a train. In this we get here the 0th data, that's been the first index. Okay, in fact I could have got that with the help of the data train 0 instead of getting that with the data frame itself. Although this one is also fine, perfectly fine, no issue. So in this we need to get here these tokens. All right. So this is token. Now you can ask a question that this is already tokenized. Then why do we need tokenizer? Okay, so this is pre-tokenized version. So in the pre-tokenized version, you have to also you have to pass this pre-tokenized data with the tokenizer as well, so that your tokenizer can understand that where it need to add CLS and separator. So we need to pass this data. I give it as data 0, the name of this as a data 0, and then I pass here as inputs equal to, instead of that, let's go ahead, give the name as inputs. Sorry, this should be data. Okay, so in this inputs, I'm gonna call here our tokenizer. It's something like this, tokenizer, and in that I call here inputs. Okay, so if I pass this and then if I print here these inputs, then you see here what happens here. So after passing this, I see that our input token got tokenized in many ways. And then if I see our tokens, then what happens here, it has CLS, EU and separator. So what happens here, it has actually, it has taken your individual tokens as a single sentence, and then again it has tried to tokenize those as well. All right, so that's why you see this EU only used as with the CLS and a separator. So to get this whole data as a single tokenizer, how would you do that? For that, you have to say that here each is split into words equal to true. That's mean our data is already tokenized, something like this. So model do not need to tokenize these individual words again. Now if you do like that, you will be seeing here a cleaned version of the input tokens here. Now it's something like this. So these one are your original token IDs, in fact these as well. So from there to here, these are the original token, but this and this, these are the separator and CLS token that you can verify here with tokens. I have taken another detailed video on HuggingFace. You can watch that, my previous video on YouTube. There you will get to know that you will get to know more about the HuggingFace. So you have here input tokens, then CLS EU reject German called by called British lamb. Now in this lamb, and there you get the separator and then CLS, these got added before and after your sentence. All right, that's how this works here. Okay, now let's compare this with our original data. So here we have our original data. In this you see there this lamb. So lamb was used as a single word, but after tokenization, this lamb got actually divided into two words. So now there is a problem. So the problem is alignment. So alignment problem has incurred here. Earlier what we had seen there, this was our STR 1, 2, 3, 4, 5, 6, 7, 8 and 9. So there are total 9 NER tags here. But after doing this, how many we have? If we ignore CLS and separator, you will be having here 10. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. We have NER tag only for 9 tokens, and after tokenization we are getting here 10 tokens. So there is misalignment. Now how would you do these alignment? And why this misalignment is happening? Because of this lamb token. Lamb token got converted into 2 token, so that's the misalignment has started from here. So you need to also write here a method to align these token. Now one more thing you see here. What happened here? This lamb, this LA and then this MB is preceded by double hash sign. Now we know that by the virtue of these transformers tokenizer that if double hash is there, that means these will go together. But our model as of now do not know. Our model will start throwing error because there is misalignment. So to adjust this misalignment, now we can check this with our input words as well. So if you check it, input word IDs, now in this word IDs, you will be seeing here none and none for CLS and separator, and thereafter you are having here 0, 1, 2, 3, 4, 5, 6 and 7, 7. That means it says that this and this, these two are single token. Alright, so with the help of these word IDs, we are going to align our labels. So it's a little, it's a simple code, but it might look like a tedious code to you. And one more thing, these word IDs, we will be putting there -100 word ID. Okay, why -100? The reason is here in traditional PyTorch method, when IDs are not used, then -100 is used there. Alright. Let's go ahead and write align label with token code. So we had seen previously that our data here, what we had seen, this was original data, and here the tokens got split into multiple words here. Okay, in between I had stopped the video, so I used here a print statement to print these. Otherwise there is no discontinuity and there is no change in the code. So I used here a print statement just to print it into a single line, and in this I see here this lamb is there, this got divided into 2 words, and in the original data we had just a single word. So what happened here, our token got mismatched here. Now we need to write a code to align these token. So I write here def align labels with tokens, and then I write here labels and word IDs. So word IDs are like this. Once you have word IDs, align labels with the token, labels and word IDs. What are these labels? Labels are these things. Okay. So I write here new underscore labels, empty list here, and then I start with current word equal to none. That's mean no word is selected currently. What we are going to do? We are going to iterate over these word IDs, and based on that we are going to get here their desired labels. Okay, so I get here current word none, and then for word ID in word IDs, something like this. And I write here if word ID not equal to current word. Okay, so you see what happens here. This word ID in word IDs, that means it will iterate over these word IDs. Current word selected as none. So obviously this one will be equal to this one. So this will get here. This will not get stored. Alright, this when this is not equal, only then we need to do. Okay. So for current word equal to none, for word ID in words ID, if word ID not equal to current word, that means if word ID is not equal to none or any of these, then it's going to execute this one. It says that here current word equal to word ID, like this. Alright. Thereafter, if word ID, now I'm going to write here else if word ID is none, if word underscore ID is none. Alright, when this case we got, I mean here and here, in this case we add here new labels dot append, and inside that we append here -100. So why minus 100? Minus 100 will be used because this minus 100 is used in the PyTorch as default padding when there is nothing to tag. So we use here new labels dot append minus 100. Okay. Thereafter else. Now you see there how many conditions we have checked here. If word ID not equal to current word, then I say current word equal to word ID. That means it will take this one as the current word. And if word ID is none, that means it will apply it here and here. Then in that case, new labels dot append will new label dot append minus 100. Means this and this will get replaced with minus 100. Thereafter we have here else label. I mean to say that when word ID equal to current word, that means when this 7 equal to 7. So for this particular case, we are going to write that here. So label equal to labels, and in that I get here word ID. Alright, so whatever the labels we have passed here, these are the labels. Alright, so in these labels, 7 number is here. Okay, if 7 number is here, then not this one, but in fact this one, 7, 0, 1, 2, 3, 4, 5, 6 and 7. So this will will be fetched here into label. Okay, now what I do here, if label ampersand equal to 2 equal to 1, that means it says that if this label, whatever these index we get from there, if that label is odd number, then we are going to add one, we are going to make that as even there. So I write here label equal to label plus 1. Alright, so it will make here 7 to 8 or like that. Okay, that means if this one is tagged as the beginning, then we have to make that inside of this one. That is why we do this particular line of code. Thereafter I write here new underscore labels dot append and then label. So this gets added here. After doing all these, then we return here new labels. Now this code is not complete as of now. We have completed if else and we have completed else if and then else part. This if part is still left here. When word ID is not equal to current word, I mean to say that now we need to see in these things here. Okay, so if we need to see in these things, then what we are going to do here, we say current word equal to word ID, then label equal to, if current word equal to, word ID not equal to current word, then we define current word equal to the word ID. Then we say here label minus 100 if this word ID is none, else labels word ID. Thereafter I do here new labels dot append and inside that I do here label. So what's the difference in this and in this? This is the case when word ID is not equal to current word. Current word was selected here as none. Alright, that means when word ID is not none, in that case it goes there. But later on, as we see here, current word get assigned as word ID if this one gets executed, something like this. Even in that case, we have to understand that this word ID, what we are seeing here, this is none. If this one is none, then we say minus 100, otherwise we say it as label word ID. Alright, just to make it a little bit more clear, as we are assigning current word equal to the word ID in the next iteration, this current word will be the previous word, that's been the previous one. So it's actually comparing with the help of this one, we are trying to compare. These should not be equal there. If these are equal, then this will get executed. All right, perfect. Now let's go ahead and complete this code. So I just run it. Thereafter, we need to complete this code, but before that we need to see if this alignment is correct here. So what I do here, I see here labels is equal to data train. I'm gonna get here the first sample, and in the first sample I get here NER tags. So these NER tags we have to do, first of all, we have to align these NER tags here. So you have these NER tags. Let's go ahead and get the word IDs. Okay, so I get here word IDs equal to inputs. Inputs we have already calculated, if you remember, and then we get here word IDs. Inputs dot word IDs. Thereafter we print labels here. All right. Okay. So labels are these are original NER labels, and in word IDs, in fact, we can also print here word IDs as well for the input. Now these are the word IDs. All right. So this one is the original label, and here are the word IDs. Sorry, these are the original labels and these are the word IDs. Let's go ahead and align our label with token. So I call a function which we have written just align labels with tokens. In that we pass here labels and then word IDs. If I do that, then you will be able to see it. Okay, seems like somewhere I have made a mistake while defining this. Okay, here. Everything is word ID. I wrote there words ID. All right, now run this. So if I run this, what do I get here? Okay, so I get here -100. Seems like something is wrong. It is not correct anyway. Okay, seems like this return function are not aligned here. This return is inside for loop. That's why at this first iteration itself, we had returned from the function. Okay, so now I brought back this return to as main function return. Now if I write this, I should be able to get here correct output. This none got replaced with -100. Now this 0 which we had here 3, this 1 is 0, then 2, 7, 0, 0. Now the interesting part, you need to see it here. Alright, so in original case it was 0. Now again it got replaced with 0, 0. So this will now becomes here original. Now this will modify our original labels, and then we will put back this into the data so that our data can be ready for the training. Now I write here a new method named as tokenize and align labels. Tokenize and align labels. Inside that, I'm going to pass here examples. So these examples are actually individual data points. In the trained data set which we had seen earlier, these are individual examples here. Okay, so we pass individual example and then we tokenize our data. So I write here, tokenized inputs equal to tokenizer, and in this I pass here examples, here tokens, truncation is true, and then I write here is split into words, which is also true. You see what happened here? We pass our training data sample. Inside that there is tokens. So this one tokens, we pass the token. Then we say that our token is already split into word, so do not split into other words. And then we get here the truncation is true. If our token, goes out of the maximum length, then it will truncate there. Thereafter I get here all labels equal to examples as NER tags. It's like this. We have seen here something like that. Thereafter we get here word IDs. So word ID says that word ID is equal to tokenized input dot word IDs. Once you get all these, now I'm gonna say here new underscore labels. I'm gonna provide here an empty list there for I labels in enumerate all labels. You see what happened here. All labels for, let's say this one, you have NER tag, there you get all labels. For all these labels we are going to iterate it over one by one. Once it iterate one by one, then we call that label value from here and then we put that into a new labels. So that I write as new underscore labels dot append, and then I call this particular the function from there itself. So I call it like this: align labels with tokens. I pass their all labels, I pass here labels, and thereafter I pass here word IDs, the earlier word IDs which we have got there. Alright, once you have got all these, then we store these into the tokenized input. So I write here tokenized inputs, and in that I write here labels is equal to new labels, something like this, and then I write here a function which is going to return these tokenized inputs. That's all you need to do here. Once all these things are done, now you can simply use data map function. So I write here tokenized data set. Tokenized data sets equal to the data dot map, and inside that I pass here tokenize. In fact, I need to pass here this function tokenize and align labels, and then we are going to pass it into batches. So I pass it into batches, which is the batch is true, and then we are gonna remove here some columns. So I write here remove columns. What columns we are going to remove? We are going to remove all columns, okay? And anyway, it is going to return our NER tags and the tokenized input, so we do not need other columns anymore. So we have remove columns data train dot column names. It's going to remove all column names here. Let's go ahead and run this. Now as we start running here, it says that some list seems like out of index that I need to verify first. Okay, so the mistake we have made here with the word IDs actually, because it is getting processed into the batches, so we have to make those word IDs here. And you have here word IDs, tokenized input, then word IDs. Inside that you need to pass here which particular index word ID you want to fetch here. So that's how I get here. Okay, now once you get all these, I save this, and thereafter I run this method again, and then I'm gonna run it here. So it's going to apply a map method on training, validation and test set. So it has successfully tokenized. Let's go ahead and see your tokenized data set. What do you see in tokenized data set? In tokenized data set, I get train, validation and test. In these, I get input IDs, attention mask and labels. That's all you need for the classification. You do not need everything. This is only we need for the training. Okay. And for classification and the final task, when you do the NER prediction, that's the token classification, then you have to do all these pre-processing, what we have seen previously, and then you can pass your pre-processed data for the token prediction. Okay, now our data is ready here. Perfect. All right, let's go ahead and start writing final piece of the code. We have done our data token alignment. Now we need to do the data collation. So data collation is a process where these data will be processed into the batches. Data collector for token classification is a method there available in the transformers. So I write here from, you can see here like something like this. Data collation and metrics. All right. We had seen a model building earlier from where we started model building. This is the main heading. Inside that main heading, this tokenization was done here. In fact, I should be writing here tokenization. And thereafter this tokenization process, now we are going to do here the data collation. Okay. So in the data collation, I need to do here from transformers import data collator for token classification. Once you import this one, then you can simply write here data collator is equal to data collator for token classification. Inside that you need to pass your tokenizer. So I write here tokenizer equal to my tokenizer. The name of the tokenizer was tokenizer itself, which we had written earlier. That's how you need to do. Once you do this, your data collator is ready. Now in this data collator, if you pass your tokenized data set, then you would be able to see your tokenized IDs here. I'm just going to show you here for some data set. Like you have your tokenized data set here. Inside that we have here a train. Let's say this is the first sample, and so similarly we would be having here many samples. These are the input IDs. So what I'm going to do here, I'm going to replace it with I, then I write here for I in range 2. So basically what happens, this is going to run 2 times and then I will get replaced here. You will be getting tokenized data set from the 0th index and first index. So it would be something like this. You will be getting here the 2 data set here. Do you see there the input ID here and here? That's the 2 data set. Inside that, after that, I write here batch equal to data collator, and then I pass it here. Do remember this is just sample to show you how this data collator work. So I passed here just 2 samples. In these 2 samples, now I'm able to see it here. Now do you see there whatever the data we had here, labels, these labels got introduced here. And now these are having here -100, -100. So for first one it has -100, -100. That means these will be ignored. And thereafter here you see -100, -100. These will be also ignored. So what are these things? You see, in our original data we have, this is our original data, let's say. In fact, I should be taking this whole thing from here. This is our tokenized data set. In this tokenized data set, length of input IDs is larger than the length of this input IDs. In this, one is separator and CLS. So what happened there is just 2 tokens there. Only for those 2 tokens in second list, we have 1 and 2, and other than that, we have here -100. And similarly, we have attention mask here only for 2 these middles, and then CLS and the separator, and the rest we have here 0. So that's how this data collateral works. It works in the batches. It does these truncation, it does these paddings, and also it does these replacement, what we are seeing here, a proper ID replacement. -100 is used there for our -100 is used for the, you know, this one is used in PyTorch to say that we need to ignore these tokens. Okay. Now let's go ahead and try to understand that how you can do the metrics analysis. So metrics evaluation is also very important part here. You know, in classification task, where we do a general classification task, not the token classification, not the NER one. In general classification task, we have their accuracy, F1 score, and recall and precision. In this, we also have these, but the method of calculating these are different, because here this one is token classification. Let's say you have one data, one sample. For one sample, your token have to be correct. I mean, for this whole sample, your token classification have to be correct. If any one token out of one row got disturbed, then overall error, it will be considered as whole data set is, or whole row prediction is wrong. Basically, what I mean to say here, let me just show you with some sample. I'll show you with sample. Let me first install related libraries. So we will be installing here pip install sequence evaluation. So this sec eval is used to evaluate NER task. Thereafter we have here pip install evaluate. Okay, these are two libraries. This need to be the pip. So pip install sequence evaluate and then pip install evaluate. Okay, so once these, let me just do it again. Once these are installed, then I'm just gonna comment these. Then I write here import evaluate, and thereafter I write here metric equal to evaluate.load, and then I'm gonna say here we want to do the sequence evaluation. This is not traditional classification task where we used scikit-learn classification report and we get the output. This is sequence evaluation. In sequence evaluation, it is very important to understand that all sequence need to be correct. That's what now I'm going to show you. Let's say you have your sample NER features, something like this. NER feature is equal to the data train features, and then here you have NER tags, something like that. Now you get here NER feature. Okay, so in this NER feature, this is our feature. This one is actually overall all features. This one is all feature. So in sequence classification, let's say this is your actual feature. In sequence classification, these sequence need to be exactly same for all these tokens. Only then this whole row will be considered as correct, otherwise it is wrongly classified. You cannot say that I have got all other tokens correct but only this one is wrong. In that case, in this NER, that doesn't work. It has to be everything correct. That is why this sequence evaluation is a little different here. Thereafter, I write here label names is equal to NER features dot feature dot names. Now I got here label names. Label names are exactly same like what we are seeing here in the form of list there. Okay, so you have now your label name. Let's go ahead and now get the labels of your first data set. the first data set just for the evaluation purpose, so that you can understand that how this evaluate and sequence evaluation works here. So I write here labels equal to data train. I'm gonna get here the first row, that's the 0, and then I write here NER tags. After that I write here labels is equal to label underscore names, and here I write here the first one. Okay, so you have here label names for I in labels. It's something like this. So what happened here, label equal to the data train 0. So we have got the first samples NER tag. In the first sample NER tag, these were written as numerical data. Now these numerical integer values got converted as a string. So for the first one we have organization, miscellaneous, and then miscellaneous. This is label. Now in this label, suppose that if we change something and then we calculate the accuracy, then what accuracy we will get. Okay, so I write here predictions, let's say is equal to labels.copy. So I just copied this whole thing here, and then at the second location 0, 1 and 2, at this particular location I'm just gonna change it here to equal to O. It's like this. Thereafter I do here metric dot compute, and in this case what we are going to do, I pass here predictions equal to, this one is predictions, and then I pass here references equal to labels. That's the correct one. Let's go ahead and run this. Now what output you will get here? The precision is okay, but F1 score and the recall is really low here. It's extremely low. That's the 0.2, and the numbers are, there are the total, the two in this, which we have got this one and this one. This one is, we have already set as O. So overall accuracy is low in this case when we are considering only one label. So that's how the sequence evaluation works. Now we have to write a method so that we can do these metrics calculation for our whole model. So I'm gonna write here import numpy as np. Thereafter I define here compute metrics. This takes one single parameter that I write as eval preds. Okay, now these eval pred will be having the two things here. One is the logits. The logits is kind of the output from where we get it's kind of the output object from where we get the output. Thereafter we get here labels equal to eval underscore preds, something like this. Thereafter I write here predictions is equal to np dot argmax, that's the argument max. Then you have here logits, and then you have here axis equal to 1. So you see what happened here. We got logit and label, and inside this logit we have got the predictions here. Okay, once you get the predictions, thereafter we need to remove ignored case which we do not want to include for our accuracy calculation. So we have to remove those as well, and that you can remove from the labels. So for that I write here true underscore labels equal to, first of all I need to write here for label in labels. this could be a little, you need to pay here extra attention. This is comprehensive list. So for label in labels, now you have, got here a single label, single, a single rows label that will be having a list something like this. So that's the single label there. Inside this single label, again, you have to run here a for loop. All right. So I put it here inside this again. Then again, I say here for L in label, if L not equal to -100. Do you recall our previous, the data where we had something like this? So during the calculation, we have to remove these, otherwise these will influence our accuracy, because actual data is this only. So we have to consider only these, not the other things. So we say that here, remove that -101 for L in label. If L not equal to -100, then in that case, I'm gonna get here label underscore names, and then I put here L label names. Now it will be, giving us the name here, integer name, string names here. All right, that's how you get the true labels. Now let's go ahead and do the true predictions. Thereafter, again, for the predictions, we have to do the same thing. So we have here true prediction. In the true prediction, we have our predictions here, and along with that, we have our label here. So we have to patch these together. We have to zip these together. So I write here for prediction and label in zip predictions and labels. So this prediction iteration will happen, label iteration will happen one by one. So these will be coming for single row. These are for all data set. Once you get for your just single row, then that single row you have to also modify here. Again, I have to do here a for loop where I'll zip again these prediction and label together. So I write here for P and L in zipped version of prediction and label. All right, I'm just going to put it into 2 line. So again here I got zipped version of prediction and label. These are getting read into P and L. Now these P and L are individual tokens, these are. Now again we have to check here if this label is not equal to -100, only then we have to consider these label names here. Then we consider label names here. So this will avoid any kind of the bias or influence because of those -100 predictions. Thereafter you write here all metrics is equal to metric dot compute, and then you write here the predictions is equal to the true underscore predictions equal to the true predictions, and then you have here references. In that you have here true labels. All right, in references you have here true labels. Once all these are done, then you can simply return your the all metrics from here itself. So I'm just gonna do here return all metrics. That's how we write a function or a method to compute the metrics. Okay, so all these things are done. We have reached a stage where we can say that now we are going to train model. So I write here model training task. So in model training task, you can simply write here from transformers import auto model for token classification, something like this. And then you write here model is equal to auto model equal to the auto model for token classification. Then you write here from pre-trained, and then you write here model checkpoint. Thereafter I write here id to label equal to id to index to tag. We already have that, in fact. Okay. Thereafter, in fact, we have to calculate, we can calculate here the new one actually. So I can write here id to label equal to something like this. For I and label in enumerate label names. So we have used label names earlier. Okay, so these label names are here. These are the label names. I'm going to write here id to label. So which one is for I label in enumerate label names, and then I need to prepare here dictionary. So in this dictionary I write here I and then label. This one is id to label, and then you can simply write label to id as well. So label to id, and here I write label and I. So like this, I and label, and then label and I for I label in enumerate label name. That's how we do this here. id to label, I'm gonna just give this particular thing here. If you want to check that what is this, you can check. But before that, we have already defined model checkpoint at the start when we called our tokenizer. So it's going to download that model. Once all these things are done, you can check here id to label. So what do you see here? id to label. It is something like this. Okay. All right. So we have our model now, which we have got from model checkpoint. Now you can check model.config dot number of labels. How many number of labels are there? Total number of labels we have passed into our model, that is 9. Now we are ready to train our model. So we got our model as model for token classification, and we have already defined that model checkpoint. Perfect. Now I need to do here from transformers import training arguments. Thereafter you can write here argument is equal to training arguments, something like this, and then you write here DistilBERT fine-tuned NER. So I'm giving here a name which we will be using to store our checkpoints. That is the name of the model. Thereafter we are going to provide here evaluation strategy. That's the number of epochs. Then there I also say that it need to save on every epoch. Thereafter I say here learning rate is equal to the 2 e power minus 5. Thereafter I say here number of train epochs equal to 3, and thereafter we say here weight underscore decay 0.01. So see what happened here. Training arguments, DistilBERT fine-tuned NER, evaluation strategy, epoch, save strategy epoch, learning rate 2 into e power minus 5, number of train epochs is 3, and weight decay. Well, it should be something like this. Okay, so that's how argument is there. Now we need to just pass this argument into the trainer. So I write here from transformers import trainer, transformer import trainer, and then I write here trainer is equal to trainer, and then inside this I pass here model equal to model, and then these arguments which we have just got here as argument, and then we need to pass here train data set. You know, I'm writing it quite fast because now the things are very much clear. If you are reading, if you are seeing this, or if you are watching these HuggingFace tutorials, so I'm 100% sure that you are very much comfortable with machine learning technologies and machine learning codings. So these things are pretty much straightforward to you. Train data set equal to tokenized data sets. This is the tokenized data set which we did with our data collateral. Okay, so with the data collateral we got the tokenized data set. In that, the train data set need train split. Thereafter we say here eval data set is equal to tokenized data set, and in that I pass here validation data set. It's like this. So we have got tokenized data sets for train data set, and eval data set needs validation data set. Thereafter I pass here data underscore collateral is equal to data collateral. So all the information is also stored in this data collateral, and then in this compute matrix is gonna have here compute underscore matrix. It's like something like this. Thereafter we have here tokenizer equal to the tokenizer. Trainer dot train, we are going to run it something like this. Okay, so now you see your model has started training here. Seems like all our code are correct and your model has started training. So now what you need to do? If you remember, I told you earlier that we are going to use our machine runtime as a CPU. On CPU, it's going to really take like a lot of time to train this model. Now, this is the time when we can change our runtime. So I'm going to change our runtime to T4 GPU. Obviously, it is going to disconnect current machine. Then I'm perfectly fine to disconnect our current machine. It's going to connect this new one. I'm perfectly fine because our code is 100% correct now. We do not need to worry about anything. We have written our code perfectly. Now you need to just go in runtime and then just run all. You need to run everything at once. That's all you need to do. Since our code was perfectly fine, there is no fear to check that if this will run correctly or not. It's going to install necessary libraries which we have seen, but I think we have to stop this and we have to run it again, because here I had actually commented this one, so it will not install that one. Along with that, if we scroll it at the top, Okay, all these it will install. So seems like I have to just restart it and then run all. Otherwise that which two packages I had commented, those will not get installed. Okay, so it has restarted. It is initializing compute engine. Once initialization is done, it will start running and then it will start installing all the necessary packages. It will again download the data, it will do the tokenization, it will do all those stuffs which we have seen previously. Seems like it has got some error, which is perfectly fine, no issue at all. We are just going to run everything from here. Just run everything. Alright, so we have to wait here for some time because running it first time on a GPU server, it's going to reinstall everything. It will download data, it will download model, and then it will reach here. It will start training our model. So I'm just gonna wait for a while. Thereafter I'll continue this lecture. Alright, so the model has started training here. Now it is connected with the GPU, so it's going to just take a 4 minutes per epoch. And we are training it only for how many epochs? It's just a 3 epoch. So obviously it will take less than 10 minutes. Alright, seems like our model has stopped in between. It has thrown an error and it says that some input variable with inconsistent number of samples. So seems like we have missed something somewhere, and I doubt that. I might have missed something while model building, perhaps here. Okay, so model equal to the auto model for token classification dot from pre-trained. Then I write here model equal to the model checkpoint. Obviously this is correct here. There is nothing wrong here. I'm just gonna put here some tabs so that I can bring it here. And then I have here ID to label equal to the ID to label. Another thing is missing here, label to ID. And in that I'm gonna give our label to ID as well. Something like this. Okay, so our model is now initialized here correctly. Once your model is initialized correctly, you can simply run everything here. Alright, just below that model, training arguments, and thereafter I'm going to again run our trainer.train. So it's going to start this training once again. It's going to take 3 to 4 minutes to complete the training. Previously, it got stuck after 1 minute. Alright, seems like once more this error is here. Okay, so we need to fix few things here in compute metrics. In compute metrics, prediction equal to the NP org max, logits axis should be -1. Along with that, these return all metrics, I need to just modify this so that I can rename all metrics keys there actually. So it takes here a precision, but our all metrics have a key value here which is written as overall precision. It's written like this. So we have modified this one. This is for precision, and okay, this is for precision. Thereafter we need to write for recall, and then I write here overall recall. Thereafter we have to write it for F1. Then we have to write here overall F1. Then we write here accuracy, all metrics. Thereafter we write here accuracy. Alright, so we have here precision, all metrics, overall precision, recall, all metrics, overall recall, F1, all metrics, overall F1, and then we have here accuracy, all metrics, overall accuracy. Okay, once these things are done, then I'm just gonna run this cell, and thereafter I'm moving to model training, and then from transformer, model config, and then here we come. Okay, So now the training has started. Again, it's gonna take a few more minutes. We have just modified 2 or 3 times our code. Okay, let's wait for training. Alright, so the model training is done here and seems like loss is very less and validation loss is also very less, and seems like precision, recall, F1 and accuracy is quite good. So this doesn't seem satisfactory. The problem is here again in the compute metrics. I'm sorry, it's 2-3 times I actually changed the code. In label names, it need to be here a P. That's the prediction one. Otherwise, it has taken this labels one, and because of this label one, it was actually making true label and true prediction almost equal. But it should be here a P. Thereafter, you need to just run this compute metrics once again, and then you need to just come back here and then you run your trainer one more time. Okay, now it has started training. We need to again wait for 5 minutes so that it can finish training. Now you can clearly see here F1 score, accuracy and the recall has been started printing correctly. So accuracy 97-98%, recall is also quite good. We have to just wait for a few more minutes to complete this training. Alright, so the final part of the training is being done here. The third epoch is just done and we are getting almost 98% of accuracy, which is really quite good accuracy. So our fine tuning of model is perfectly done. Now our task is to see that where our model fine tuning is stored. So the model fine tuning is stored here. Do you see there? So this model fine tuning is stored here. You can use any of these model just to test your final prediction. Now you can also download these fine tuned models so that you can use these for your later purpose. I'm gonna import here auto model for token classification, which we already we have to do here the prediction, in fact, not the auto model. So from the transformers, import pipeline. Thereafter, I'm going to create model underscore checkpoint is equal to the model checkpoint which we are going to use. So we are going to use this particular model. Alright, so inside this the trained model data is stored here. So we are going to use that one, and then I'm gonna give the path of that model path. Thereafter I say here token underscore classifier equal to pipeline, and inside this pipeline I give here name of the pipeline, which I say as token classification, and then the model is equal to model underscore this model checkpoint. In fact, I'm gonna give here the checkpoint, the name as checkpoint itself, and then I give it as checkpoint. Alright, that's the model checkpoint. And then aggregation strategy. So aggregation strategy is used to give you the output when you have multiple tokens, so these will be combined together. I give here name as simple. Alright, that's the aggregation strategy. Once all these things are done, then you can simply write here token underscore classifier. Then you can give here the name. So I write here my name is Lakshmi Kant Tiwari. I work at KGP Talkie and live in Mumbai, let's say. Let's go ahead and run this. We are gonna run this. Seems like some error is there. Unknown token classification task here. Okay. Seems like here something is wrong. Okay, the task is here, token classification. Okay, perfect. So it says that Lakshmikant Tiwari is identified with the 99.9% as a person, and then the KGP Talkie is identified as organization, and then this Mumbai is identified as location. Now you see, it's so simple. It's so simple. Now you can give any text data. It will give you those 4 entities: person, organization, location, and miscellaneous. Alright. Now you can feed any kind of data, be it for search, be it for resume parsing or CV parsing. Once you have your data, you can use this particular code to run your algorithm. Now the final task is left here. You need to just download, this one. You cannot directly download it from here. You need to just zip this one. After zipping, you can download. It's very much simple. If you want to zip it, you can simply run here zip and the target file name. Let's say target file name I want to give here DistilBERT NER .zip, and then you also need to give here the file names which you want to zip here. So I just give this path here and you just run this. After running this, you should be able to see here DistilBERT zip NER, and then you can simply download this file from here itself. Once this file is downloaded, then you can, okay, seems like this one is incomplete. Wait a second. Okay, zip, and then I think I have to give here -r just for recursive zipping here. So it's adding all these files which we have seen there, and once all these are added, then you can simply download this file. All files are now added. Now you can check that this DistilBERT NER.zip. Alright, so you see there all files are added. You just refresh this. You have here DistilBERT zip NER zip, and then you can download this. So this will be quite large file. It will take a time to download this file. Once this file is downloaded, then you can extract it, and then you can get started with prediction. Alright, this is all about in this lesson. Thanks a lot for watching this. If you have liked this tutorial, please like this video, subscribe this channel, and share this video with your friends and on social media. Alright, I'll see you in next lesson.